everybody out there in YouTube land. Good times for all, or Zachary Zabala here if you prefer. The date is, I don't even know, 24th, I think. Sorry about that. Yeah, February 24th, 2019. Hope you're all having a good day, all that good stuff. I'm sorry it didn't go live. I was, let me move some stuff around. All right, bear with me. I got some bad news about my uncle Friday. Kind of put me in a funk. Didn't feel like going live. But I had some stuff I wanted to do this morning and talk about with y'all. I wanted to start testing the electric field. I've been doing some research into how they do it, and a lot of it seems really math-based. Trying to think of a way to get it up there and have somewhat control and knowing your elevation and altitude, whatever you want to call it. I'm not sure. I'm still kind of baffled on how I'm going to do it. We're going to do some live research here, though. We're going to go looking. We're going to go looking on the internet for how they measure the electric field. Electric field. By altitude. Or I'll just put elevation. Yeah, when you're searching, there's so many different words you can use that it's a good idea to try different phrases. Don't just put one in one search thing. Like I did, how to measure electric field with elevation. You could put measuring the electric field with elevation. Measure the electric field by altitude. Hey, Constance, how we doing, darling? Hope you're having a wonderful day. Showing refer to blah, 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 blah. Is your real measure of fair weather, electric field, and current. Let me see. I don't want to pull up a... I got to figure out how I can show you people what I'm looking at without sharing my screen. I've never done that. I don't want to look at Wikiversity. Blah, blah, blah. See atmospherics on high altitude balloons. Yeah, I do love a good sunny day. Okay, we're going to go to Caltech. It's not a PDF. Hey, welcome. ISAGT 57, good afternoon. I hope you're having a wonderful day, friend. I'm just looking up how to measure the electric field with altitude. Why I'm doing this? There's been a lot of talk about gravity. what gravity is and what causes it and how it happens. And I am very much under the idea, at least. I have an idea that, and this isn't my idea, this is something that was told to me by Walter Lewin, former MIT physics professor, that everything is held to the ground. Actually, I'm going to play it for you. Why do I sit here and try telling you this stuff when I can actually just play it for you? Come back to this later. We're going to open up another one. Here we go. Walter Lewin. Eight 0.02 Lecture 1. Here we go. Okay. And at right around 40 minutes or so into the video, I mean, I could watch it over and over again. I've watched this video, like this one, at least 5 or 6 times, if not more. Electric charges and forces. Coulomb's law. That's the name of this person. Hey, Just Jack. How we doing, brother? Hope you're having a wonderful day. Just looking up how the electric field works. Actually, I'm going to I should turn off my camera maybe. Then you just be looking at my thing.
I'm Walter Lewin.
He is Walter Lewin.
My lectures.
His lectures are amazing. 32 minutes, 34, 36.
9 times 10.
See, that's why you have to almost skip through a lot of the stuff. It's just, you don't have to, but I just don't understand it. It's a lot of math that I cannot comprehend. I'm going to see if I can share this with you. Please let me know if I'm giving away whatever.
Thank goodness the nuclear forces are not part of 802, so I'll leave that alone for now. So what holds our world together? Well, on the nuclear scale, 10 to the minus 12 centimeters, very important are the nuclear forces. On an atomic scale, up to thousands of kilometers, it's really electric forces that hold our world together. But on a much larger scale, planets, stars, and the galaxy, it is gravity that holds our world together.
Now, did you hear what he said there?
Now you may say, that's what you just told us. Because didn't you tell us that D cancels? Gravity is electricity.
Yeah, did you hear what he said? I mean, I don't want to get a copyright strike, but this is all,
And the acceleration that
fair use act. We're going over this, but this is the gobbledygook that I don't really care for too much. All the theoretical math. But he does a lot of test observations and maybe even experiments.
10 to the minus 12 centimeters, which is 10
that,
to the minus 14 meters.
I mean, you can go. I have my Fun with Electricity playlist, and that's all me doing the test observations and experiments, 4 or 5. It just starts getting expensive, some of the toys that he starts playing with. But I mean, I have an electroscope, I have a Van de Graaff generator, I have Tesla coils, an electrophoros, I have the rods.
So what holds our world together?
Listen right here.
Well, on the nuclear scale, 10 to the minus 12 centimeters, very important are the nuclear forces. On an atomic scale, up to thousands of kilometers,
thousands of kilometers hold our electric.
Planets, stars, and the galaxy, is gravity that holds.
Okay, did you hear that?
Together.
Now this
Now you may
is,
say, that's very inconsistent with what you just told us.
this is him coming out and saying, here, we'll go back and listen just 10 seconds. I don't know if I can, nope, can't do it on this thing. Come on.
Holds our world together. Well, on the nuclear scale, 10 to the minus 12 centimeters, very important are the nuclear forces. On an atomic scale, up to thousands of kilometers, it's really electric forces that hold our world together.
Up to thousands of kilometers. Up to thousands of kilometers. It is electricity that holds our world together. Okay, very important. Now this next part is see, he doesn't lie. At least not about he's even said that in one of these. It's within the first 5, I guarantee. It's in one of the first 5 videos. He says he is testing, he's putting 2 electrodes inside of a hollow sphere and testing if there's any electric there. He is actually touching them and pulls them out. And he says, I did touch, I cannot show you, but I would not lie to you. Not about this. So he is pretty much saying, in my eyes right there, that he is going to lie to you, or he has lied to you about something. So he is a very honest person. I think what he says in that spot is that he is being forced to lie. But this next line right here is so important. I believe this is 100% truth. Yeah, exactly. Macro and micro. Well, right here he says it. Gravity controls the sun, moon, stars, planets, galaxies, not holding us to the earth. He just said electricity holds the earth together, and for thousands of kilometers. That is electricity in their globe model. This is what drives me insane, is that people do not. They're still talking about mass attracting mass, or Newtonian, or Einsteinian, about things holding us to the earth. When right here, an MIT physics professor comes out and says, hey, it is not gravity that is holding you or anything else to or the earth even together. It is electricity. Yeah. Yeah, and I think he's been threatened about this because he's made 2 videos where he about the flat earth, about how he is not going to discuss this conversation. And if you don't like him for it, then that is fine. That's okay. If you don't want to be his friend anymore, that's okay. He forgives you. He was almost telling you, I cannot talk about this. But he had to go. But listen to this next line. This next line says it all. When it's about the lights above our heads. They already outed this guy and he lost everything. They said he was a pedophile. Now, did they do that to one of their own that's playing by their rules? No. He had to do something or say something to be outed and thrown underneath the bus. Yeah, neutron nonsense. Exactly, Just Jack. But this next line right here, it's going to say it all. This next line is what I want people to understand, that gravity only deals with the lights above our heads. They were trying to figure out how they could make it all work. But as far as everything that we know today about, actual real science that, has been tested and experimented on, and has laws behind it. Electricity holds us to this place. Now, I'm not exactly sure how it all works. Me and Adam have been talking about, well, here, I'm going to play this first real quick.
Yeah. But on a much larger scale, planets, galaxy, it is gravity that holds our world together. Now you may say, that's very inconsistent with what you just told us. Because didn't you tell us that T cancels? Compare gravity with electricity. Yes, but keep in mind that most objects in the universe have only a very small amount of charge per unit mass. The Earth and Mars have each a charge of about 400,000 coulombs.
Okay, what he's going to be explaining right here is why, mathematically, the way they have it all set up, that gravity doesn't start taking place until you have two very large masses. You can't have one gigantic large mass and then a really small mass next to it, teeny tiny, stuck to it, and say that that's gravity doing that. Gravity, it takes two large masses to have an attraction to each other. Here, he'll start explaining that and how it eventually, once they get big enough, and I believe distance has a lot to do with it, then these forces start becoming much more powerful than the electric forces that are involved.
The gravitational force between them is therefore about 17 orders of magnitude larger than the electric force. So even though our immediate surroundings are dominated by electric forces, including your own body, for that matter.
Listen to that. Did you hear what he just said?
The behavior of the universe on a large scale is dictated by gravity.
Oh, I love it.
Than the electric force. So even though our immediate surroundings are dominated by electric forces.
Even though our immediate surroundings are dominated by electric forces. For those of you who just started, I want to go back to show these a few new people that jumped in what we're actually talking about. I think this is so important. But anyway, I lost my train of thought now. I got to quit looking at that kind of stuff. We'll just keep going. The immediate forces around you, hey, Flatlander, are dominated by electricity. Okay? They are just everything around us, even our own bodies. Everything is dominated by an electric force. He is very adamant about the way he speaks.
Including your own body, for that matter. The behavior of the universe on a large scale is dictated by gravity.
The universe. So here on Earth, the only place we can go to and measure and, gather real data, the only place that we can do all this stuff, this real science, actually yes, exactly. Just Jack. Micro and macro are mathematical fairy tale. Yes, just like the way that they measure the electric field. Which is why I'm talking about this right now. I'm telling you, it took me at least 3 times to watch this lecture 1 to understand what he was saying. And it's not because I I didn't understand or comprehend what he was saying, it was because he would say something and it would get me so enthralled and thinking about it that I would miss the whole rest of the video. He'd be talking, but I'd still be just blown away and brainstorming by what I had just learned. And then I'd go back and watch it a few days later, and I'd get to that point, and then I'd hear something else on the next one, and then I'm, boom, blown away again and not contemplating what he was actually saying later on. So, yeah, I love listening to him talk about this stuff, though. But yeah, those of you that were here at the beginning, you heard it. He says flat out that electricity controls. Actually, we're going to go back a little bit because he talks about the micro, macro, and how the atomic forces and how they have no clue what is making. No, not the cosmic background. Well, yeah, I guess it is. I guess, yeah, exactly. The cosmic background radiation, but really it's flow, the flow of the electric field and its intensity at different altitudes and elevations. Weed Man, what's up? But it's electricity that holds the world together. And as Just Jack was saying, the micro and the macro, all that stuff, that all of this that we know of, that we can actually measure and test here, that we have, you know, that you and I can go out and buy this stuff, that they're little, you know, atoms. Actually, right here. God, this lecture is so flat world logic. What's going on? This lecture is amazing. Fair Use Act. I don't think Walter Lewin. I mean, we're just discussing what he's teaching. Yeah. Yeah, I think we're going to go over a lot of these because, man, he talks here. I hope he doesn't, you know, take offense to any of this, me using his.
My lectures will, in general, not be a repeat of your book, but they will be complementary to the book. The book will support my lectures, and the lectures will support the book. You will not see any tedious derivations in my lectures, for that we have the book. But I will stress the concepts.
Yeah, Just Jack, exactly.
The equations, beyond the concepts.
And that's what he does. Okay, Walter Lewin is an amazing teacher. Hey, Josh Corey of the Iron Realm. Happy Sunday, cuz. Dave, how we doing? Yeah, the Thunderbolts project. They just, they drive me nuts. They have it so close. And if they would just apply it, because I'll tell you why the Thunderbolts project doesn't work, because they have their model on a globe. And when you have a sphere shape, like the ionosphere, okay, for example, no charge, positive or negative, is going to gather on the inside of a sphere. And we're going to go over that eventually, one of these days. If I can keep going through these lectures without getting copyright strikes or anything like that. Hello, hello, hello. What? Ho. Travis, welcome. But God, there's so much about electricity that this guy can teach us in just like 4 or 5 of these. And I've watched them all like 5 times, but I'm thinking we're going to go through but he tells you right here, he's going to teach you to see beyond the equations. And he actually shows you, and you can you can actually understand what is happening in the world of electricity and how it actually works. This guy changed my life. He really did.
Show you whether you like it or not, that physics is beautiful. And you may even start to like it. I suggest you do not slip up, not even one day. 802 is not easy. We have new concepts every week.
Comes one of my buddies.
And before you know, you may be too far behind.
Oh, I got the door closed.
Magnetism is all around us. We have
Electricity and magnetism is all around us. Hey, big boy Cephas, what are you doing, buddy? Hi. Hi there, guy. What are you saying? What are you saying, babe? Sorry, guys. I gotta say good morning or hello to one of my good buddies. Hank's big pal, huh? Yeah, there's Hank and Panker. That kiss was for you, Constance.
lights, electric clocks. We have microphones, calculators, televisions, VCRs, radio, computers. Light itself is an electromagnetic phenomenon, as radio waves are. The colors of the rainbow in the blue sky are there because of electricity, and I will teach you about that in this course. Cars, planes, trains can only run because of electricity. Horses need electricity because muscle contractions require electricity. Your nerve system is driven by electricity. Atoms, molecules, all chemical reactions exist because of electricity. You could
I'll let him finish.
See without electricity. Your heart would not beat without electricity. And you could not even think without electricity. So I realize that even with electricity, some of you may have a problem with that.
So pretty much, he is saying that electricity, if you heard, it controls everything. You couldn't see, you couldn't think, you couldn't move. Horses couldn't run, light wouldn't be there, radio waves wouldn't be there. Electricity is everything. It's everywhere around us at all times.
The modern picture of an atom is...
Okay, did you hear that? He is very, very... This guy is... Oh, I love him. The modern picture of an atom. The modern picture. Now watch, he'll go on to say that we don't know what they look like. So all these people that say, well, atoms do this and atoms do that. You know, you tell me, say, show me an atom.
A nucleus, which is very small compared to the size of the atom. The nucleus has protons, which are positively charged, and it has neutrons, which have no charge. The mass of the proton is approximately the same as the mass of the neutron, is about 6.7 times 10 to the minus 27 kilograms. The positive charge is here with the nucleon, with the neutrons.
Come on.
And then we have electrons in a cloud around it. And if the atom is neutral, the number of electrons and the number of protons is the same. If you take one electron off, you get a positive ion. If you add an electron, then you get a negative ion. The charge of the electron is the same as the, that's why the number is the same for neutral atoms. The mass of the electron is about 1,830 times smaller than the mass of the proton, therefore negatively small in most cases. All the mass of an atom is in the nucleus. if I take 6 billion atoms,
Blah, 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 blah.
touching each other, I take 6 billion because that's about the number of people on Earth, then you would only have a length of 60 centimeters. Give you an idea of how small the...
So they say 6 billion atoms lined up next to each other. If you had 6 billion of them, it would only be about 60 centimeters.
Atoms are. The nucleus has a size of about 10 to the minus 12 centimeters, and the atom itself,
now listen right here,
times larger, particle of electrons, is about 10 to the minus 8 centimeters. If you line 6 billion of those up, you only get this much. Already in 600 BC, it was known that if you rub amber, that it can attract pieces of dry leaves. And the Greek word for amber is electron. That's where electricity, well, it's named from. In the 16th century, there were more substances known to do this. For instance, glass and sulfur. And it was also known and written that when people were bored at parties, that the women would rub their amber jewelry and would touch frogs, which then would start jumping of desperation. People considered it to be fun, not understand.
They were torturing these little frogs with electricity. I believe that they knew exactly what they were doing.
And what actually was happening to the amber, nor what was happening to the frogs. In the 18th century, it was discovered that there are two types of electricity. One, if you rub glass, and another, if you rub rubber or amber, for that matter. That's called one A and the other B. It was known that A repels A and B repels B, but A attracts B.
So he's just talking about positive and negative. They didn't give it. See, I think people don't get the whole positive, negative. They look at, I don't know, because we have other words that apply to these. And negative even gets a minus, you know. It's not like it's hard to explain. Let's see what he says here.
And it was Benjamin Franklin, without any knowledge of electrons and protons, who introduced the idea that all substances are penetrated with what he called electric fluid.
Okay, all substances are penetrated with these, all substances. Everything has electricity in it. Now, it may be a neutral charge. It may be, you know, stable, but it still has a charge there. A charge can be manipulated on it by applying another, you know, or even putting another charge near it. You can actually separate these charges on these, and he'll show that. It's really neat.
Electric fire. And he stated, if you get too much of the fire, then you're positively charged. And if you have a deficiency of that fire, then you're negatively charged. He introduced the sign convention, and he decided that if you rub glass, that is an excess of fire, and he called that, therefore, positive. You will see later in this course why this Georgie at 50% chance is extremely unfortunate, but we have to live with it. So if you take,
so what did he say there? Did he say he was wrong?
And bring it from one substance to the other, then the one that gets an excess becomes positively charged, but automatically, as a consequence of that, the one for which you take the fluid becomes negatively charged. And so that's the whole idea behind the conservation of charge.
So in order for something to get a charge, it's just like heat or pressure. In order for something to get a higher pressure or a higher heat or a higher positive charge, something else has to become less pressurized, cooler, or negatively charged. Electricity is just like all these other things. It's a yin-yang effect. It's a balancing system that we have. And when certain things, the video volume is low, let me see. I have it, let me see. It's maxed out. I don't know what else I could do. I could try putting in headphones and see if that helps. Give me a sec.
But you cannot create charge.
Is that any better?
If you create plus, then you automatically create minus.
So the conservation of energy. You cannot create charge unless something else has a charge taken away from it.
Plus and plus repel each other, minus and minus repel each other, and plus and minus attract. And Benjamin Franklin, who did experiments, also noticed that the more fire you have, the stronger the forces. The closer these objects are to each other, the stronger the forces. And there are some substances that he noticed which conduct this fluid, which conduct this fire, and they are called conductors.
Okay. So he said something interesting there. He said the closer that these two objects become, the stronger the charge can get. Let's see, we'll just go back just a hair, just a sec. Where am I at? I'm going to make this full screen again. I don't even know what I did there. I messed up. Nope, there we go. Cool. Okay, computer's running a little slow. Just give me 1 second, folks. Come on, Walter. There we go. I'm just going to jump back a hair and try to listen to this part right here.
You have, the stronger the forces. The closer these objects are to each other, the stronger the forces. And there are some substances that he noticed which conduct this fluid, which conduct this fire, and they are called conductors. If I have a glass rod, as I have here, and I rub it, then it gets this positive charge that we just discussed. So here is this rod, and I rub it with some silk, and it will get positive.
If you want to try this, hey, rose-tinted monocle, welcome, ma'am. If you want to try this, I learned that a lot of this stuff you can go to a store somewhere and buy much cheaper than you can get at a scientific. I spent like $50 on my rods and stuff like that. I thought they were going to be, these nice big ones like he got. I didn't even look at the sizes and this and then they came out and they were like these little 8-inch, which I mean they still work. They still do what they're, but you don't have to go to them to get your scientific equipment, your testing equipment. You can make most of this stuff yourself out of stuff that you can find or just go buy and purchase and then put together yourself. Let's see. So he's talking about the electrostatic rods right here. I've got videos on this where I did this.
What happens now to an object that I bring close to this rod? And I will start off with taking a conductor. And the reason why I choose a conductor is that conductors have a small fraction of their electrons which are not bound to atoms, but which can freely move around in the conductor. That's characteristic for a conductor, for metals.
Now remember, when he's talking about all this stuff, he's talking about theoretical things like atoms and stuff like that. So don't, you know, it's hard to, it's more like a fluid. Think of it like Benjamin Franklin said, there's a fluid, not these little tiny things called the electrons. And so many of them can move around and so many of them can't, and this or that, and yada, yada, yada. Pay no share or no mind to that. Think of it like the air. Electricity is just like the air, but electricity can penetrate everything. Think of it as like a wind that can blow and you don't feel it, but it's always there. And it's always moving around us, and it's always, I've used this analogy before. Think of a water faucet and you're standing on a screen and the water faucet is, 50 feet wide and you're standing in the middle. Well, there's a flow of electricity that is just constantly, it's flowing through you, it's flowing through everything. You can't get away from this. Even in a Faraday cage, which I don't understand, but I'm gonna start doing stuff on that. But there's a flow from the top to the bottom, and it can yeah, you can jump on, Trav. In fact, oh yeah, I wanted you to see one of these parts because it talks about gravity and electricity. Did you want to jump on, Trav? Constance? You guys are more than welcome. If not, no big deal. But I definitely want you to hear a part of this, Trav. There's a part that's important. Nora wanted you to hear it.
That's not the case with non-conductors. They are all electrons.
Let's see.
Are fixed to individual atoms. So here we have a certain fraction of electrons that can
just people
around.
We know. I don't want to let any trolls in or anything like that.
Electrons want to be attracted by these positive charges. Plus and minus attract each other.
I will only allow in people I know for a fact will not snipe me. That's it. I'm not playing the games or doing any of that other nonsense like Nathan and Dell have to jump through and all that stuff. I'm just not doing that. I don't want them on I don't even want to deal with any of that nonsense. This is, troll free zone. But yeah, anybody would be all right.
And so some of these electrons which can freely move will move in this direction, and so the plus stay behind. This process we call induction.
Okay, did you hear that now? That is called induction. But back to the subject at hand, or back to the matter at hand. Perfection is perfected at the latter. Understand. Who is that? Oh, that's Snoop Dogg, I think. From way back in the day. Okay, yeah. Here, he's going to show this image on the board again. But listen to what he says here. Induction is the separation of the electrons and the protons in a material, in this one object. Like if you had a piece of steel. Give me 1 sec, folks. I'm going to send a link out to Travis. Oh, there it is. All right, Travis. Invite has been sent. Yeah, out of one object, you can change, you can have it so one side of the object will be positively charged while the other side will be negatively charged. And he really gets into this when he starts talking about the electrophorus device, which you can go and make yourself with a pizza tray, like a piece of a coat hanger, and pretty much anything. Yeah, it's really neat. I spent way too much money on stuff that I could have made myself. But you learn, right? So here we go. He's talking about induction, not conduction. This is called induction.
You get sort of a polarization, you get a charge division. It's a very small effect. Perhaps only 1 in 10 to the 13 electrons that was originally here will end up here, but that's all it takes. So we get a polarization, and we get a little bit more negative charge on the right side than we have on the left side. And so what's going to happen?
And I can say for a fact that this is real. You can go into my fun with electricity, I think they're called, something like that. But yeah, you can. I've tested it with a electric meter. You can have one side of it will be positive, and then do the exact same process, test the other side, and the other side will be like a steel plate even. The other side will be negative. It's so cool how electricity works. It's that simple.
Hello, hello, hello.
What?
What ho?
What oh? How we doing, Trav?
Good, good. Yeah, I'm not trying to hijack anything. I just thought that because, just asking questions and clarification if it came up, because I don't remember the ones that I had 5 minutes ago. But anyway, you can carry on. I just thought it would be interesting if there was.
Yeah, absolutely.
So anyway, keep going, man. Just sit back.
Alrighty.
Since the attraction between these two will be stronger than the repelling force between these two, because the distance is smaller, and Franklin had already noticed, the shorter the distance, the stronger the force. What will happen is that if this object is free to move, it will move towards this body.
Now what I'm thinking, I'm trying to put this in a huge scale, and things that we've heard happening throughout history, things getting kind of crazy during certain times, and things being pulled up, or whatever happens, the sun falling out of the sky, the stars going away. If these things really happened and they are electric, I believe he kind of explains how all this stuff can happen in these just first 4 or 5 videos. But kind of have that in your mind when you're listening to him talk about this stuff, about how it applies to the real world, and not just in a small scale, but on a, plane wide scale. Because electricity, they say at least, it's mathematically somewhat sound. If you had a perfect environment to test in, and you did it here and it was 2, and then you doubled it over here, it would be 4. Electricity is quantifiable. And now there's all kinds of other things that get thrown in there that can change, your outcome. But in a perfectly controlled environment, electricity does have laws. And he's kind of going over a lot of that right now, how electricity works and what, just think if whatever's above us creating the positive source were to change in distance, the electric field the charge here on Earth would also change. So when they talk about there being giants or there being big things at one time, huge animals, you know, they say there was more oxygen in the air and this and that and this and that. Maybe it all has to do with a natural cycle that is actually happening, you know, with the larger scale. Just whatever is causing the positive to be moving for closer, or I'm not sure yet. But just have this kind of stuff in your minds when you're listening to them talk.
This is the first thing that I would like you to see. I have here a conductor. It's a balloon, helium-filled balloon. And I will rub this rod, silk. And as I approach that balloon, you will see that the balloon comes to the rod. I will then try to rub with that rod several times on that balloon. It will take a while, perhaps, because the rod itself is a very good non-conductor. Not so easy to get charge exchange between the two. But if I do it long enough, I can certainly make that balloon.
Sorry, I just read your question, Constance. In this world, we have flow, current, we have resistance, and we have disturbance, activity, excitement. Would you say induction is polarization that we ourselves cause? No, induction is a natural occurrence, but it's something that we can also cause on other objects. See, I think induction is taking place in us at all times. Since the ground is negative below us, if you are grounded, most of the positivity, the positive charges, will be, you know, in the bottom half of your body. While all the negative charges will be at the top, reaching out towards the positive charge above our head. Polarization is in seeds. It is in, he even shows stuff like that. Every grain of rice has a positive and negative. I think that's so they know which way to grow. Everything is based on electricity. It's really neat.
Positive, then they're both positive, and then they will repel each other. But first, the induction part, whereby you will see the balloon come to the glass rod.
So he's taking glass and silk, rubbing it with silk, creating a positive
These
charge.
experiments work best when it is dry in the winter. They don't work so well when it is humid. So it's a good time to teach 802 in the winter.
So see, the amount of humidity in the air affects electricity greatly. This is why they say Tesla went out to New Mexico to build his the new Warden Cliff Tower, the one that burned down in New York. He had figured out something, and he had to be above a reservoir and this or that, but he realized that drier climates is better for not only building an electric charge, but discharging. Hold on one second. I got Hank out there barking. See if he comes a running. I just hate him barking so early in the morning. No, it's 9:30, but still. Come on, Bubba. You don't need to be barking. You're laying down, okay? Just give him a break. You're okay. Come on up here. Lay down with Dad. Come on. Bo went inside. Come on. Come here. Come on up there. Good boy. Okay, just lay down. Take it easy, okay? Sorry about that.
Okay, there we go. This should be positively charged now. And the balloon wants to come to the glass. You see that?
So the balloon is negatively charged then. See how he's making sure not to touch it, because then he would have listened.
This balloon charged a little.
Now he's applying a positive charge to it.
That go from the balloon to the glass.
And he is using a metallic balloon because that balloon
itself, so it's not always so easy
is a conductor, like he just said.
Charge exchanges.
Whereas a rubber
Let's see
balloon,
whether I have
which
succeeded
is
now in making the balloon positively
it'll
charged as
absorb
well as
the
the glass
charge.
rod. If that's the case, then the balloon is not going to like me. The balloon will now be repelled. And you see that very clearly. To show you now that there are indeed two different kinds of electricity, if I...
So he showed you there that the balloon was negatively charged, and he can discharge and put a negative charge on an object just by touching it himself. He can ground it out, which means that it's got the negative charge to it. And then when he applies the positive, it goes to it. But then when he took the rod and rubbed it a few times and applied it to the balloon, and then rubbed it a few times and applied it to the balloon, he was taking some of those electrons that they say, or the electric fire or fluid, and letting it absorb onto that balloon, therefore making it positive. And then when he took the rod, which is positive, and put it towards the balloon, it then was, pushing it away.
I now rub with cat fur. By tradition, we do that with cat fur. I don't know why. By tradition, we use silk for the glass. So if we do this with cat fur now, then this becomes negatively charged. Remember, there were two types of electricity. And since that balloon is positively charged, now the balloon will come to me. And there it is. Now it comes to me. So you've seen for the first time now clearly that there are two different kinds of electricity. The positive charge.
And I did all these. You can go check them out on my channel. I did that demonstration right there. That was one of the first ones I ever did. And I actually polarized a rubber balloon. And I played with it for a few days, messing around with it.
Charge chosen by Franklin on the glass rod and the negative charge on the rubber. So now you may think that if I approach a non-conducting balloon with a glass rod, and I have a non-conducting balloon here, you may think now that this balloon will not come to the glass rod because there are no free electrons. So these electrons cannot freely move, and so you don't get this polarization, you don't get this induction. But that is not the case. And this is actually quite subtle. You have to look now at the atomic scale.
Okay, so what he's saying now is, now we're going into jibber jabber mathematics, made up nonsense that we had to create to explain why this next example, this next observation takes place. He's going to the atomic scale now.
Okay, so can I jump in real quick?
Yeah, absolutely.
Okay, so you have, on the one hand, it seems that you endorse what he says, and on the other hand, you just said jibber jabber. So I'm trying to understand where you're making a delineation for yourself in terms of what you are holding on to and what you are letting go of from his perspective. Right? So earlier he was talking.
Yeah.
Earlier, so he was talking about atoms and whatnot, and I think that I couldn't hear him very well, so it's just listening through you. So were you making the comment that we can't observe atoms, or did he make that comment?
No, he goes into it in his whatchamacallit, the gravity lectures a little bit more. But he pretty much says that this is the common model that we understand. He said this isn't something that we have ever seen with our eyes.
Okay.
Like an electron going around the proton and the neutron. Yeah, I know they've showed little fuzzy dots and they say they're atoms and this and that. But what he's saying is the actual model.
Right. Okay.
That's right. He says it's our common picture.
Right,
That's
but
what he
it's not
said.
only that, but also at the level of elementary students and middle school students, I interpreted that as if this is bona fide, factual, observable stuff on a microscopic level. So even though it's too small for the eye to see, well, they must have seen it at one point, even with the help of an instrument.
Well, I mean, he's talking about atomic, theoretical,
Yeah.
pretty much.
Okay.
Things that they don't even understand yet. He'll
But
come
you've
up and
got
say that
models-
here.
But you've got models that represent ideas.
Yeah, just
Okay.
like the globe, you
And-
know?
Yeah. Right.
Yeah.
Right.
So that's why I don't take any of that. I'll listen to it and put it under consideration, but it's not like law to me.
And so, what point is he at right now that you critiqued him with jibber jabber? Real quick.
He's talking about the atomic scale now, the atomic level, things
Okay.
taking place on an atomic level. Yeah.
So I guess what we're trying to, again, what we infer. Are you still there?
Yeah. Yeah.
What we infer is things that we see on a macro level. So we see electromagnetic reality in our world on a macro level, and so then we deduce or infer that continues down on a smaller and smaller and smaller and smaller scale, right?
Yeah. Oh, I understand the concept. Same thing with it getting bigger and bigger and bigger.
Right.
But the thing is, there's certain things that are different at those scales, you know, different pressurizations, there's different variables with the different scales. You know,
So
things are different at each level. None of the levels are exactly the same with all the different dynamics that take place in this wonderful creation.
And so one of the things that I was thinking earlier with what was being said, I guess, it made me think of what you and I have talked about and what you've said before, but an electromagnetic attraction is gravity, right? So if you're going to suggest...
No, not electromagnetic. No, those are two different things. The electromagnetic field is one thing, and the electric field is another thing.
Okay.
They're two totally different things. And that's what he's talking about, the electric field right now. He gets into the electromagnetic field here later on in the course.
Okay, all right.
I believe that's like 5 or 6, yeah.
Okay.
Yeah,
all
no,
right.
in this one, he's just talking about how electricity flows from one thing to another, and magnetism hasn't even come into the conversation quite yet.
Okay. Carry on.
Yeah, these are just baby steps.
If I take an atom that you have here, you have positive charge, and you have the electrons here in a cloud around the positive nucleus. If I bring a glass rod, positively charged nearby, then these electrons, which are stuck to the atoms, they cannot freely move like in conductors, however, will spend a little bit more time on the side where the glass rod is, because they feel attracted by the glass rod. Whereas the nuclei, if anything, want to go away from the glass rod. So what you're going to see is that, in a way, if I started off with a spherical atom, let's suppose this were a spherical atom or a spherical molecule, then what will happen is that you get sort of a shape like this.
Did you hear that? Let's suppose it's a spherical atom or a spherical molecule.
And the electrons spend a little bit more time here than they spend here. And that means that I have actually polarized that atom. If the electrons spend more time on this side of the atom than on this side, I have also created the phenomenon of induction, and I therefore expect that this side becomes more negative than that side. And I can show you that in a nice way with a transparency whereby I have plus and minus signs, and
yeah, he's going to show you here that this is just all on paper. This is all the theoretical stuff he's talking about when he's talking about atoms, and then he'll show you a demonstration on why they came to this conclusion. But again, it's kind of like the globe. It's, you know, if P then Q, how does Nathan do it? P therefore, or however he does it, you know. That, how does he do it, Travis? If P then Q.
It's usually if P, then Q, P, therefore Q. If I'm full, I ate pizza. I'm full, therefore I ate pizza.
Okay, yeah.
There's two different arguments. There's a positive and a negative. The positive, I think, is modus ponens, which is if P, therefore Q, and then the negative is the opposite. If not, then not, and that's modus tollens.
Okay.
But anyway, if that's what you're going for, the if P, then Q.
Yeah,
P,
yeah, that's pretty much what he's doing right here. Is just saying, well, we see this happen in these balloons, so on an atomic scale, in every atom, this is what we say is happening. You know, that's his logic.
equal number of plus and minus signs. So they represent neutral atoms. There you see them. Boy, a little dirty, but maybe see I can clean it a little. Okay. Where are okay. So here we go. So notice there are equal amount of pluses and minuses. So think of the plus and the minuses as one neutral atom, just a representation. Now I'm holding a glass rod on this side, which is positively charged. And so each atom, the electrons want to go a little bit to this side, and so the nucleus stays behind. And if each atom does that, this is what's going to happen. And now notice what you end up with. In the middle of the substance, plus and minuses cancel each other out again. But on the right side, you have created a negatively charged layer, and on the left side, you have created a positively charged layer. And so in a way, you have again induction. So even in the non-conducting objects, this side will turn negative, and this side will turn positive. And therefore, if I approach a non-conducting balloon with a glass rod, I will also see the balloon come to me. And so I can easily show you that. It doesn't make any difference whether I choose glass or whether I choose rubber. I can do it with both. Non-conducting balloons always have a potential problem. The potential problem is that they can be charged by themselves, just like the metal balloons can be charged by themselves. However, if I touch the metal balloon, then any charges there will immediately flow through me to the earth. We will understand that later, because this is a conductor. Remember, the electric fluid is conducted by a metal, but not by a non-conductor. So with this, it's more difficult. Even if I kiss it and touch it, it's not clear that I can take all the charge off. In fact, by doing that, I may even make it worse. Let's hope that it is not charged too much, and let's approach it with this glass rod and see whether I can convince you that indeed it's coming to the rod. Not because of the free electrons, but because of that process. Oh boy. Oh. And it should also do the same with rubber.
It'll push it away because it's a negative.
I hope. If it were negatively charged, it go away. It does go away, so it is negatively charged. You see that? By touching it, I actually probably charged it. There's not much I can do about it. Very difficult to get charge off.
Yeah, once I did this to that type of a balloon, it stayed polarized for days. In fact, I should have just kept doing it. Eventually I just quit messing with it. I jumped onto something else.
I guess though my question is we don't have any direct empirical experience of things like this in our world. Like for me, on a macro level, I don't ever see this happen. So, you know, if we're going to talk about this in the same way that we talk about scientific evidence, this is a man-made construct that he's demonstrating something that doesn't happen naturally. It might, I mean, there might be electricity, and he's manipulating the elements. So, you know, you can watch a magician levitate a dollar bill between his hands, and you don't realize that he's electrically charged the trick, so that he's got electricity levitating the dollar bill, but you don't know that. But you also don't ever see that anywhere. So I guess I'm just trying to think through, and I'm not disputing anything. I'm just thinking out loud in terms of, you know, what exactly are we trying to establish and maintain by what he's showing us. You know what I mean? Because nobody walks around doing it with a Mylar. No one else does this with a Mylar balloon, so to speak.
No, he'll show you other examples of what, not just the balloons. I mean, taking off your clothes. If you have on a polyester shirt, if you turn off all the lights and stand in a dark room, when you go to take that off yourself and pull it up, you're going to hear crackles and you're going to see sparks.
Yeah. I get that. Sure. Okay.
Combing your hair, even.
Right. Yep.
You can, if you know, you can make sparks and crackles.
Yeah, it's just static electricity. So again, he's showing us a different manipulation of that phenomenon.
Yeah, just he's kind of baby stepping you through just how electricity actually can, you know, how there are two different forces in electricity, and they attract each other. But if you have two of the same force that aren't together, they push off each other. They don't want to be connected.
All right. Well, that's why I brought up the issue of magnetism, because that's the same in the magnetic field.
Yeah, but there's a little bit more to magnetism. He gets into it.
Yeah, I mean, I suppose, but that's where my
magnetism is like the storing of electricity.
Sure. Yeah. Sure. Right.
Naturally,
I think I was just drawing some analogies in my mind in terms of electricity and magnetism. In terms of the positive and negative, I was noting the correlation in my mind. So that's where I mentioned.
Oh yeah, it's huge. There's such a. I mean, you can't have one without the other, really. Electricity and magnetism kind of go hand in hand. Everything that produces electricity puts off an electric field. It's one of those things. So here we'll see. Let's go ahead.
I already had a suspicion when I approached it with the glass. It was too eager to come to the glass. Still negatively charged. That's the way it goes. It's not because the demonstration failed, but it's because the balloon is charged and doesn't want to give it up because it is a non-conductor. Friction can cause electric charge. And that's exactly what happened when I touched this balloon and tried to discharge it through friction. I may actually have charged it. If I take these party balloons that all of you may have seen on your shirt, on your trousers, they stick. They have charge on them, whether it's positive or negative, I don't know. I don't even remember. Not important. And so when I bring them to my hand is not a good conductor, but you get inducted.
Did you believe that, what he said right there?
When I listen to the Hangout, it's not as loud, so can you just restate it?
He said there's a charge on the balloon. I'm not sure whether it's positive or negative. I don't really remember. It's not important.
Okay. What's significant about that for you?
Not so much as the significance, it's just the way that he says it. I'm trying to pick apart him. I've been really analyzing the way he moves, the way his facial expressions are when he says certain things. Like if I think that he's lying about something, I really pay attention to what he's doing.
Okay,
it's probably a lot harder without being able to see him actually say it and stuff.
So
Let's play it one more time.
You're almost saying like he's just blowing smoke. You know,
because he has to, pretty much, yeah.
Right. Again, because we don't know.
Yeah, remember this guy was outed. He was blackballed. He was thrown under the bus. I mean, we know how many pedophiles there are out there, right? In high places. And if he was one, you know, chastised.
I'm sorry, what's the connection with pedophilia?
Walter Lewin he was blackballed and kicked out of MIT, and he had all his credentials pulled for being a pedophile, supposedly.
Oh, okay.
Yeah, or something. Maybe not pedophilia, maybe with just a student. I'm not sure, but I'm pretty sure someone had mentioned pedophilia. And they don't do this to their own, you know. So either he came out and said something, or they were, I don't know.
Okay.
But yeah, I think he knows more than he teaches and lets on to his students, for sure. So
okay.
I'm trying to read him pretty much. But
Yeah,
if you can. Yeah, he actually has a YouTube channel. He puts out questions all the time and quizzes, and yeah. He even talked about flat Earth a few times. Check out his video, something about the master. Whether you agree or disagree, with the master, it does not matter, or something like that. He mentions flat Earth. About how he is not going to discuss this topic, because I'm sure there's a lot of people bringing it up with him.
Yeah, I'm sure.
And he says he's not even going to touch it. He will not discuss it. It's okay if you don't like him anymore. If you don't want to be friends, it's okay. He forgives you, but he will not discuss this topic. He has said it blatantly. So I think he's been told, you know, been warned, I'm sure.
Yeah.
But yeah, listen, if you can, it just doesn't sound genuine. It speaks with such compassion, you know, about this subject, about physics. And this part, he's like, I don't know, maybe, who knows, I forget. It's like, come on, Walter.
Yeah, okay, I follow you.
See what happened when I touch this balloon and try to discharge it through friction, I may actually have charged it. If I take these party balloons that all of you may have seen, and you just rub them on your shirt, on your trousers, they stick to my hand. They have charge on them, whether it's positive or negative, I don't know, I don't even remember, not important. And so when I bring them to...
For the people that are watching, did you see his face? His face got all scrunched up and he had a big frown on his face when he said that. Oh, I don't know, blah, 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 blah. It just screams to me that I'm being a deceiver right here. If you read a couple books on reading body language and stuff like that, his whole face just scrunched up like he wanted to attack almost, like he was getting ready to bite. Like he hated what he was saying right there. It was weird. Okay.
My hand is not a good conductor, but you get induction, this phenomenon that we just discussed. And so the two attract each other. The positive and the negative side attract each other. You can stick them on the ceiling. You can stick them on the board. You can decorate your room that way. Very pretty, isn't it? All of that you can do now because of 802. Now, these heavy balloons may be a little bit more difficult. Also, I'm wearing cotton. If you wear nylon or polyester, it's much better. It's much easier to get. Oh, that's good. That's a nice one. I think we need a blue one.
Yeah, just a great teacher. Just
there we go.
Mixing in
So
a little bit of
friction
humor with everything.
Causes electricity. That's, of course, why the silk, when we rub the glass, and the cat fur, we rub the rubber, then we create charge on one. Of course, if you make the glass positively charged, your silk will be automatically negatively charged. When you comb your hair, you may have noticed with dry weather that you hear some cracking noise.
And if you, when you do this, when you rub the rods, it makes crackling noises, just like he's going to show you here with rubbing a rubber comb through your hair.
Noise. Cracking noise means sparks. You will learn all about sparks in this course, though not today. But you can hear.
Oh, this is Walter Lewin. He is a former MIT physics professor. I believe this was from, I'm not even sure, 2011, but don't hold me to that. It may be, or sure.
Hear it if you're very quiet. And as you do that, you charge the comb. I can hear the cracking. Interesting. So the comb is now charged, probably, so am I. There it comes. Not as good as the glass, but same idea. If you take your shirt off and you make it dark in your dormitory, and you stand in front of a mirror, an amazing experience. And I'd be happy to do it for you because, but I told you I already wear cotton and it doesn't work with cotton so well. You really have to do it with a nylon shirt. And when you take that nylon shirt off, not only do you hear the cracking, but you actually see the glow of these teeny, really little sparks. You actually are like a light bulb. It is an experiment that you cannot miss. And I would suggest you try that this weekend. And do it with a friend, that's even more fun. We all perhaps remember when you just walk around, do your normal things during the day. There are rugs in the room, want to leave the room and you touch the doorknob, and you get a shock. Spark that flies over, the electricity. Even when you touch a person, you sometimes feel this shock. When you cook and you take saran wrap of these rolls, the damn stuff just doesn't want to come off because as you roll it off, there's friction and it gets charged and it often gets crumbled up. It's very bad, very difficult to handle it. You've all experienced that. Also, cellophane around boxes with chocolate, the same thing happens. As you take it off, you charge it, whether you like it or not. I now want to do an experiment. I need a volunteer. I need a student who actually is wearing, preferably.
Now, all right. See what Nathan Oakley would have to say about this.
Not all cotton, but I think, Simon, you have a beautiful, wonderful nylon. You are willing to sacrifice a little bit for the sake of science and come over here and sit down here. Just relax. Make sure that your feet are off the ground. Okay. So what I'm going to do now, Simon, I'm going to beat you with a cat fur.
This is the stuff that just made him.
And as I beat you with cat fur,
great.
You will get charged. And since I don't want you to be the only person.
I'm just going to stop you just for a second. I just want to do a little short rant. When you're going to teach young kids, make it fun. Make it interesting. Use colorful, vivid analogies that they can relate to. If you were up there, standing up there, talking like this, and blah 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 blah, people would tend to, zone out. When you are educating people, take a note from Walter Lewin. Throw in a little bit of comedy, some examples, some demonstrations, and make it fun. Make it like, speak about it as though you love it and you want them to love it. I love this guy. He is an amazing teacher. Sorry about that.
Person who suffers under this experiment, I will also stand on an insulated stool. So if you become, for instance, positively charged, I don't know whether it's positive or negative, I would get the other amount of charge. So we share in the charge. And as I beat you, you will charge up more and more, and I will charge up more and more. And then we will have to convince the class that we are both charged. And we will do that in a way that will be hopefully rather convincing. Let me just start beating you a little bit to make you feel at home. We know each other, right? Okay. Now, of course, as I mentioned to you, these experiments work well when it is dry. And so if you are too wet, it won't work. But let's see, if you sweat a little bit too much, then it doesn't work too well. So you ready? In my hand, a neon flash tube.
I want one.
And although we don't know yet what voltage is, because we will learn about that in this course, to get a good flash out of this, you need about a few thousand volts. And so we will see, and we'll make it dark shortly, and I will hold the flash.
Now, when he says a few thousand volts, I know some people are like, oh my gosh, that's crazy. That's nothing. Okay, when it comes to electricity, now a few thousand volts of current, but just a few thousand volts all by themselves, nah. I got a video here on YouTube. It's in my playlist, Fun with Electricity. I take a 250,000 volt shock. It zapped me pretty good. But yeah, you can take, when you're talking about just volts, it's not like the stuff that comes out of your 120 volt wall socket. That's a current. This is just potential energy. Yeah, the amps is what you gotta watch for.
Flashlight, the flashlight in one hand, discharge tube, and then Simon will touch it on the other side. And if we succeeded, then you may see some light. So Simon, look at me first. Don't touch it yet, because we're going to make it all the way dark. You know where it is? It's there. Okay, make it dark, Marcos. Touch it. Touch it. Okay, thank you.
I love that. I love
have some light.
The examples that he does.
Thank you very much.
Now, I know you couldn't see. Would you have called that an experiment? lost Travis. Not sure. But
I think I would have called it a demonstration.
yeah, me too.
I mean, you know, because ultimately the experiment is to reduplicate an observed phenomenon that's not, you know what I mean? So
yeah.
he simply demonstrates. It's the same thing as if he showed the Mylar balloon thing again. That's just simply a demonstration of something.
Yep, I agree.
Equal charges repel each other. I've shown that the demonstration with the balloons. Here we have an instrument which is called the Van de Graaff. It's named after Professor Van de Graaff, who invented it. It was an MIT professor. And this instrument, which I will not discuss in any detail now, but you will understand it later on in the course. I'll tell you all about it later. Think of this instrument as a super amber rod. And although we don't know yet what voltage is, I mentioned already.
Oh, come on, baby.
The 20,000 volts between Simon and me. In this instrument, you have to think in terms of several 100,000 volts. And is not without danger. But that, of course, makes it more exciting to work with it. So it's a super amber rod. And what I will do first now is to put some confetti on top. And when we turn on the Van de Graaff, the confetti may at first go to the charge dome, it is already on top of it, and when it picks up some of the charge, it will then spread out because it will repel. So let's get some light on there.
No, I didn't see that, Constance. I'll have to check that out. Okay, now what he's saying is, think of this as a giant amber rod. Now, the Earth is a sphere, right? Which kind of looks like the top of that thing. And the Earth is negatively charged. No, he's going to add a positive charge to this. And you're going to see what happens. And once induction is going to take place, to where it's going to get so positively charged at the bottom, and there is, it's going to actually start pushing this stuff away from it, because both of the objects are positively charged. Because the objects weren't grounded. There was no place for them, to lose that positive charge. So kind of think of this as like reverse gravity right here almost.
Here.
I'll definitely check him out, Constance, for sure.
See. Let me put some of this on top. It's just regular confetti, pieces of paper. All right, now all I have to remember is how to start the most of the action has already occurred. I will put a little bit more on.
Scared to go up too close to it?
You see sparks, don't worry yet.
I'd love to have a Van de Graaff that size.
On.
Wow, he really loads it.
Nothing left for the second class. Make it perhaps a little darker.
Yeah, now watch this when he hits this switch. All these things go flying off instantly.
Ah, that's too dark. Okay, we'll try it once more. Give it a zap. So look at the confetti on top. And I think it's quite convincing. Some of the confetti will stay there. Well, that's for reasons that it's not a good conductor. And so it gets first sucked in, and if it doesn't get charged out, then it will not spread out.
See, I don't understand that part right there. I understand. Some of it went flying off, and others stayed stuck there, he said, because it didn't get the charge, because it wasn't a good conductor. I don't know, it's weird to me. But did you see how some of them were bouncing off and going way out and then coming back in and then bouncing off again? And they were like dancing around. That's kind of induction right there taking place.
All right. So now, let's try for the first time to be.
Hold on, Hank's going crazy again.
A little bit more quantitative. If I take two charges, and we use in general, we use for charge the symbol Q. So here we have Q1. And
now he starts getting into math. I'm going to go grab
Q2.
A cup of coffee real quick. I'll be right back.
Let's say that they are separated by a distance r. You stay in here. Okay. And the unit vector in the direction from 1 to 2, I call that r roof 1, 2. The roof stands for unit vector. If these charges are equal, both minus or both plus, then they will repel each other. And so here there is a force, which I call 1, 2. This is the force onto due to number 1. And since action equals minus reaction, force here.
Yeah, this is the part where I start
magnitude, but 180 degrees in opposite direction.
zoning out a little bit.
Coulomb, a French physicist.
Yeah, I'm going to wrap it up here soon. I'd like to jump forward, but I don't want to miss any of the good stuff.
Who did a lot of research on this in the 18th century, actually. Coulomb found the following relationship, that the force is proportional to the product of the two charges. So it's Q1 times Q2 times a constant, which nowadays we call Coulomb's constant, K, divided by the distance between these charges squared. And it is in direction of the unit vector that goes from 1 to 2. This is the force on number 2 to 1. And notice that this equation is sign sensitive, because if
Yeah, see, this is all the
Q1 and Q2 are both negative, the force is in this direction. And if they're both positive, it's also in this direction, as I have it. However, if the
sorry about that, folks.
if one is positive and one is negative, you get minus this direction, so this force flips over, and that one then obviously also flips over. In the SI units, in this course, for the unit of...
I'm going to skip ahead a little bit. This is the part that makes it hard to keep watching and keep... When he starts getting into all the math goobity gob that frankly, I don't really understand it. I never really... And when I see it, I'm sure I could understand it, but I'm not inclined to want to comprehend that stuff. You know, I don't know how else to put it. It's just, I'm more interested in the physical aspect of all this stuff than the actual mathematical concepts of it all. I'm going to jump ahead just a little bit and see what he's doing. And he's still writing on the board. There, scoot ahead a little. Yeah, he's going to be writing on the board for a little bit. The part I really want to show you guys is coming up here in a few minutes.
K, 1 divided by 4 pi epsilon 0.
Epsilon 0.
There is nothing magic about that.
You'll hear that a lot.
It's just a historical reason.
Epsilon 0.
And so 1 divided by 4 pi epsilon 0 is 9 times 10 to the 9th. That's all that matters. It has a name. It's called the permittivity of free space. But you can forget about that. It's not important to name. Notice that there is a clear parallel with gravity. Newton's law of gravity, that the force, which in that case is always attracting, gravity never repels, is the product of two masses and the gravitational constant, and again you have the distance square. So there is an enormous...
That's where it really comes into place, is the distance squared. Now he's going to start explaining about the difference between gravity and electricity and how we observe it here on Earth. This is very important. This is what I wanted you all to see. He's starting to get into it. And in a few minutes, he just says it, that the Earth and everything, you know, is held together for thousands of kilometers by electricity. Not until we come to the planets, moons, stars, and solar systems, that is when gravity, the lights above our head, is when gravity comes into play. Even in their own mathematical terms and stuff. He'll show it mathematically how it works.
Parallel between the two is the great beauty that electricity acts in a way that is very parallel to the way that gravity works.
Electricity acts parallel to the way that gravity works. So to me, that's them saying that, yeah, gravity, this force that we didn't really understand or know, is really just parallel. They work.
Yeah, that's what I was saying earlier when I made that connection.
Yeah, we can throw the whole idea of gravity out the window, because gravity only comes into play when dealing with the lights above our heads. And we don't know what those lights are. And only in their model is gravity needed.
Right. When you step off the Earth in your mind, when you step off the Earth and the things that are empirical, you can only go into math.
Mm-hmm.
You know, when you can't explain the retrograde motion of Mars, you've got to make it a diagram and then represent what you're seeing with numbers and squiggles and another language.
Yeah, another language. And like I said, they have all these variables that are not You know, like the sun being 3 degrees below the horizon already when you're starting to see it set.
Right, or when it's rising, it's above the horizon, but the light hasn't reached you yet.
Yeah, yeah, by 3 degrees, that's just insanity. That's like the distance of 6 suns stacked on top of each other. You know, it's just crazy. Yeah, because one sun length is half a degree on average.
Half
So
a
that
degree of
sun is
what?
already half a degree in the arc in the sky. Like if you take a sextant, or you can just take your thumb, is about half a degree, I think, at arm's length, and you hold it out and block out the sun, or maybe it's a different finger. Yeah, but then you add 6 of those up, that would be 3 degrees right there.
I'd rather just say 3 thumbs.
Yeah.
Or whatever. It's about 6
Yeah,
thumbs.
I hear you.
You know, like they used to measure horses, right? 24 hands, or
yeah,
14
yeah.
hands, or whatever. Because isn't that what the measurement too is? Isn't like a hand breadth at the horizon an hour?
I think so. Yeah, 4 degrees. Yeah.
Yeah, 4 degrees is 1560. Yeah.
Yeah, that's wild. But yeah, that's, you know, the sun's already up that high in the sky. You just haven't started seeing it until now. That makes no sense to me at all. But it has to be that way in their model.
Yeah, but isn't that where we go, or we loosely in air quotes, isn't that where we go in terms of talking about the apparent distance and the apparent appearance of the sun for us even, you know? It's like, that's apparently where it's at.
Yeah, but we're not saying that it's, you know,
definitive.
Physically, yeah, 93 million miles away in a ball of burning gas. We're
Right,
very open to say we have no idea what it is. Yeah, we see it right there in the sky from our position, but where it actually is and what we don't know. They're making a definitive statement. No, it's there, but you're seeing it right there. Okay, I don't know how we got off on that, but I forget where he's at. It's gonna get, oh yeah, gravity and stuff. It's gonna get real good here.
If I added a third charge, for instance here, Q3, and if now I want to know what the force is on Q2, then I
Come on, baby.
use the superposition principle, which we've used many times in 801. And we say, okay, the net force on number 2 is the force due to number 1 plus the force from number 3. If number 3, if this is positive and this were negative, then this force would be in this direction. F1, F3, 2. And then the net force on number 2 would be the vectorial sum of these two. Is it obvious that the superposition principle works? Not at all. It's not at all obvious. Do we believe in it? Yes, we do. Why do we believe in it? Because it's consistent with all experiments that we have done. But the superposition principle, which is very powerful, really not a matter of course. But it works. We can always use it, and we will.
And we will.
If you compare...
Oh, come on.
801.
I'm just going to pause it for a second. And I know I have my stuff, my camera closed down. I don't know what else to do.
With 802.
Got too much open for the old bird. Well, I can close down this YouTube and look at the chat in my... That's what I'll do.
Gravity. you will see that electric forces are way more powerful than gravitational forces.
Okay, did you hear that? Electric forces are way more powerful than gravitational forces. That's an important part of what he's going to explain right here. At least here on Earth, at the distances that we are apart.
And the way I can best show you that is by taking two protons, which are a distance d apart. Here is a proton, and here is a proton, and they are separated by a distance d. They repel each other. And the force by which they repel each other is, of course, extremely easy to calculate. We know Coulomb's law. That law is called after Coulomb. And so the force, the electric force with which they repel each other, this is just the magnitude now of the force, is the charge of the proton, which is 1.6 times 10 to the minus 19, but I have to square that. I have to multiply it by Coulomb's constant, which is 9 times 10 to the 9th, and I divide it by d squared. That's the electric force. If I want to know the gravitational force, which is the force with which they attract each other, these are repelling forces, but I just want magnitudes here, then I have to take the mass of the proton, is 1.7 times 10 to the minus 27. I have to square that. Remember, m1 times m2 times the gravitational constant. The gravitational constant in SI units, 6.7 times 10 to the minus 11. And I divide that by d squared. If now I compare the electric force with the gravitational force, so I divide one by the other, notice that the d cancels. They both have d squared downstairs. And so you will easily be able to show that this ratio is roughly 10 to the 36. So the electric force is 36 orders of magnitude more potent than the gravitational attraction.
36 times more than the gravitational attraction here on Earth. Electricity is holding us together and down into this place 36 times more than gravity can, according to their math. Here, he'll explain it even further.
This teaches you some respect, perhaps, for 802. If these were the only forces that acted on the protons, and you bring them in the nucleus, which has a size of only 10 to the minus 12 centimeters, then the acceleration that the proton will experience is the electric force divided by the mass of the proton. F equals ma, basis of 801. And if you take this electric force, when you make d 10 to the minus 12 centimeters, which is 10 to the minus 14 meters, and you calculate this ratio, you will find that it is 26 orders of magnitude higher than the gravitational acceleration on Earth. 26 orders of magnitude higher. So you wonder, what the hell holds the nucleus together? Tremendous force on these protons. Well, what is holding them together?
Okay, listen to this part right here. He's talking about protons, neutrons, electrons, what's holding an atom together pretty much. This is, he says it all right here.
Together are the nuclear forces, which we do not fully understand, but thank goodness the nuclear forces are not part of 802. So
we do not fully understand, but thankfully they're not part of 802. So that's why I say when it talks about the micro and the macro, It's theoretical.
What's 802?
Electricity and magnetism. 801 is Newtonian gravity. It's just the lecture at MIT, or the course, the physics course.
Oh, okay.
801, 802, 80, you know.
Yeah, okay.
Yeah. Here he goes.
Well, I'll leave that alone for now. So what holds our world together? Well, on the nuclear scale, 10 to the minus 12 centimeters, very important are the nuclear forces. On an atomic scale, up to thousands of kilometers, it's really electric forces that hold our world together.
All right, did you hear that?
I wasn't paying attention. I was doing something else.
All right, this is like, you got to hear this part. I don't know where I'm at. I might jump back a couple seconds here.
The nuclear forces are not part of 802.
Okay, yeah, listen to this part right here.
So what holds our world together? Well, on the nuclear scale, 10 to the minus 12 centimeters, very important are the nuclear forces. On an atomic scale, up to thousands of kilometers, it's really electric forces that hold our world together.
Now, did you hear him?
Yeah.
Up to thousands of kilometers. It is electric forces that hold our world together.
And those electric forces are multi-times stronger than gravity.
Yeah. Multi-times stronger than gravity. At least 26 times stronger than gravity. Now he'll talk about gravity right here.
But on a much larger scale, planets and stars and the galaxy, it is gravity that holds our world together.
So when it comes to the lights in the sky that we can't go to and measure and touch and, you know, then gravity comes into play. But gravity does not come into play down here on Earth. That's not, you know. This is what I was trying to get through on Nathan's when Xander jumped on that first time and was talking about gravity. He says, all right, the gravity does not affect us here on Earth. It doesn't hold us to the Earth. Electricity does that. Gravity only comes into play when it comes to the lights in the sky. At least that's how I took it. Did you hear it maybe a different way?
This has been so abstract, I wouldn't be able to say definitively. I'd have to go back and listen to it again.
Yeah, like I said, I had to listen to it like 4 or 5 times before I really wrap my head around all the different stuff that he says in here. I'll play it one more time. Just this part. I think it's just so important for everybody to hear. So on the subatomic scale, when it comes to atoms and stuff like that, it is the nuclear forces that hold everything together. And they don't understand the nuclear forces completely. And he's happy because he doesn't have to teach that in this class. That's pretty much what he said. He's like, we don't understand how everything gets held together. The weak atomic force, the strong atomic force. We don't understand any of that stuff and how it actually works. On an atomic scale, up to thousands of kilometers, so things we can actually measure up to thousands of kilometers, it's electricity that holds everything together. And not until you start talking about planets, moons, stars, and solar systems, gravity come into play. And he'll almost say it verbatim.
Higher than the gravitational acceleration on Earth. 26 orders of magnitude higher. So you wonder what the are the nuclear forces, which we do not fully understand, but thank goodness the nuclear forces are not part of 802, so I'll leave that alone for now. So what holds our world together? Well, on the nuclear scale, 10 to the minus 12 centimeters, very important are the nuclear forces. On an atomic scale, up to thousands of kilometers, it's really electric forces that hold our world together. But on a much larger scale, planets and stars and the galaxy, it is gravity that holds our world together. Now you may say, that's very inconsistent with what you just told us, because didn't you tell us that D cancels if you compare gravity with electricity?
Yes, but keep in mind that most objects in the universe have only a very small amount of charge per unit mass. The Earth and Mars have each a charge of about 400,000 coulombs. The gravitational force between them is therefore about 17 orders of magnitude larger than the electric force.
So even though our immediate surroundings are
Oh, sorry. Here, I'll let him finish. Our immediate surroundings.
dominated by electric forces, including your own body, for that matter, the behavior of the universe on a large scale is dictated by gravity. We will use various instruments to measure charge in a quantitative way. And one of the instruments that you will see, we will use it often in the lectures that are to come, is called an electroscope. It's a very simple instrument. In general, it is just a conducting rod. It could be aluminum, metal, and at the end are two pieces of tinsel, two pieces of aluminum foil. And often there is a nice knob here. And if I touch this with a charged object, then because this can conduct electricity, it can conduct the fire, as defined by Benjamin Franklin. If I touch it with an object which is positively charged, then this object will become positively charged. If I touch it with an object which is negatively charged, it will become negatively charged. And you see now here, these two very light pieces of aluminum foil will repel each other. And so you will see that this shows a certain angle. And the more charge there is, the larger that angle. So that gives us a way of doing some quantitative measurements. There are other electroscopes which are not too different. There's one central rod, and they would have one leaf hanging there. And when you charge that one up, then this leaf will go out, and if charge is more, it will go out even further. I don't have an electroscope now here, but what I want you to see that if I charge myself up and I hold in my hands these Christmas tree tinsels, that in a way, if I get enough charge on.
Now this is what makes Walter Lewin so great. His experimentation, or his demonstrations, and the comedy that he brings. So again, one more time, if you're going to be teaching people, anybody, adults, children, whoever, try to make it fun. Try to have fun while you're doing it. It's so important. That's why he was such a great teacher, is such a great teacher. He is still here on YouTube. Lectures by Walter Lewin. They will make you love physics. That's the name of his channel. If you just type in Walter Lewin, you'll be able to find him. He is an amazing gentleman, still making videos here on YouTube.
Then these tinsels will spread out. It's an idea that immediately follows from the fact that you get a certain amount of charge, whether it's negative charge for me or whether I'm positively charged, that doesn't make any difference. These tinsels will spread out. And of course, the best way I can do that is if I charge myself
with the Venn diagram. And as I said earlier, experiments of this nature are not entirely without risk. And so there's always the possibility, of course, that I don't survive this demonstration. But don't worry, because in that case, there will be someone else who will lecture 802, except he is not likely to show this demonstration again. So you might as well take a close look, because this may be the only time you'll ever see it. So I will give you some nice light on the Venn diagram. And it's always a scary moment for me. Sleepless nights. It's about the Venn diagram.
I'll let him finish. This is
Marcos, or you have the courage to turn it on. You will turn it on? Okay, hold it, Marcos. This is too close for comfort. You ready? Are you nervous?
That's the grounding rod.
See you. So look at the tinsels. And try not to look at me, please. Go ahead.
His hair even stands up.
I am now a living electroscope.
About 300,000 volts plus probably running through him right now.
If the weather is cooperating today, and if I had long hair, you might even see that my hair would start to act like an electroscope. We can try that too. Why don't you throw it?
Making it fun.
Is it
You
working?
know.
Okay, well, this weekend, make sure you take this nylon shirt off in front of the mirror and enjoy the experiments at home. Don't try this ever. See you Friday.
And that was Walter Lewin, lecture number 1 of his 802 physics, electricity and magnetism. Maybe we'll start going through these. I don't know if it'll always be Sunday. I don't know. We'll see. But it'll be during a Crocheters Corner. I'm not gonna put anything about 802 electricity in there. I don't want to try to not get a copyright strike. It is under fair use, and we were critiquing it and talking about it and all that kind of good stuff. So what'd you think, Trav? You still there?
Yeah, it's good stuff. It's just very abstract and heady. You have to watch it, like you said, over and over again.
Yeah. It's I love that he does a lot of demonstrations and stuff like that. I just think that's so cool. But like you said, it's not science. These aren't observed phenomena we see in nature.
Right. It is natural. It is nature oriented, but it's manipulated phenomenon to demonstrate something that we typically can't observe and see. You know what I mean? It's kind of like I suppose the way it makes sense to me right now is if we wanted to demonstrate wind, we would have to create a model and use a fan and then paper streamers to show the effect. But that's not saying that somewhere in our world there's this giant fan. You know what I mean?
Yeah, exactly. Yeah.
So
yeah.
you can only go so far with models, right? So
yeah.
you know,
These are observations.
I think that that's an interesting way to say models aren't reality, because I can build a model of wind, but that doesn't mean I believe that that's what is real in our world.
Well said.
You know what I mean?
Yep. Do you have anything else?
No.
Good stuff. Thanks for joining me, man.
Well, thanks for having it.
Yeah. Oh, yeah. We'll go over lecture 2 here. I'll make sure I get a hold of you before I do.
All right, yeah, and if I'm around, I'll definitely check in.
Sweet. Sounds good, man.
All right.
Thanks again, Trev. Talk to you later.
Until next time.
The Red Hen Radio. All right, that's it for me too. It was fun. We'll try it again next weekend, hopefully. Maybe it'll be the next Crocheters Corner. So if you see Crocheters Corner, I'll try to give a little bit of warning for next time. Thank you for everybody in the chat. Constance, Midnight Gardener, what's up, man? Good to see you. Bumbaclack, Gato Fish, awesome stuff. Really enjoying your chatting. Everybody that stopped in. Flat Earth Dude, what's up, man? Sorry, I had to move my chat away from the computer, and I put it on my phone, and I was kind of concentrating on the computer there. But glad to see you. Stop by. Everybody that swung by. Yeah, that was fun. Real fun. We'll try to do it again next weekend. Maybe sooner. I don't know. We'll see. But good times for all here. Signing out. As always, thanks for watching.